The degeneracy can be, as we saw previously, can be expressed in terms of carrier density and the magnetic field. So degeneracy is carrier density in the sample times h over EB. So every time nu is 2n plus 1, where n is integer, the Fermi level is in Landau level, and we have this spike in the density of states. And what would that mean? If we use just a naive Drude model, we have our conductivities and E mu. So you will have the oscillations on the conductivity because n, so I was using actually ns, so ns. So this density of state oscillates, so the carrier density changes as well, and you will have the oscillations in sigma, or in the conductivity or in the resistivity oscillates is 1 over p. And I'm talking about a longitudinal conductivity, or rho xx. So if you have a sample, and usually the samples, they are made in the form of whole bar. And it's designed like that. And then there's a material, a two-dimensional electron gas is usually carved in the form of this bar with 6 contacts. Those are metal contacts. And this is a two-dimensional electron gas. And you pass the current along the channel, and then you can measure the voltage drops. So there will be a current, and then you can measure a voltage drop along those channels, along between these two contacts, and you can define the rho xx as V over J. Now this case is Vxx. And the current goes along the x direction as well. Because of the magnetic field and the cyclotron motion, the conductivity and the resistivity, those are tensors, and they have those are 4-component tensors. So you will have sigma xx, sigma xy, sigma y, yx, and sigma yy. And the sigma xx and sigma yy for isotropic samples, they are equal to each other, and sigma xx and sigma yx, sigma xy and sigma yx, they are antisymmetric. So we have this rho xx oscillates as a 1 over b, and the oscillations usually start when the product of mobility times magnetic field is greater than 1. So the mobility times the magnetic field should be bigger than 1. Let's say if the mobility is around 10,000 in volt per centimeter second, centimeter minus 2 second, then which is then can be transferred to meter squared seconds, will be 1. So approximately the oscillations would start at B above 1 Tesla for this sample. If the mobility is higher, like for graphene, maybe you will have a mobility around 100,000, then the oscillations would be at around 0.1 Tesla, and so on. Then something drastically different changes when you observe quantum Hall effect. So in the quantum Hall effect, if we plot now, this will be rho xx, and this is a magnetic field. There will be some value there, so usually it increases a little bit, and then it starts the oscillations, and then at some point you get this region where the rho xx is 0, and that's the manifestation of a quantum Hall effect. At the same time, when you measure signal across these two terminals, so when you measure voltage across those two terminals, this is Vxy, then you can define rho xy as Vxy over J in the x direction. Then these the rho xy also oscillates, and what will happen, so normally you would see the straight line, and there will be some development of features on top of this straight line, with the slope is just from the Hall effect. And then in these regions where you have rho xx 0, rho xy would actually form a plateaus, and so on. So the rho xy is a plateau, which only depends on the fundamental constants and then the filling factor. The quantum Hall effect was discovered by Klaus von Klinzig, and this constant bears his name, so it's a von Klinzig constant. And it's approximately 25.813 kilo ohms. And it's actually known to a really high precision. I think in the current measurements give you the value of 25,812.80745 and so on ohms. It's one of the most well-known constants, and that's the way to define actually the electrical charge and so on. So you can define fundamental constants. You can measure the fundamental constant using this quantum Hall effect. Because of the tensor nature of the conductivity and resistivities, at this region where you have rho xx 0, the sigma xx is also 0, because the sigma xx is can be calculated, so that's an inverse, and it should be rho xx divided by the rho xx squared plus the rho xy squared. So because rho xx is 0, the sigma xx is also 0, and the rho xy has a plateaus. You can also write the expression for the sigma xy. It's filling factor times E square over H. And it's just reciprocal because the rho xx components are 0. All right, so now let's think what it means from naive picture if we use just a Drude model. So if the sigma xx is 0, that means there is no current in the bulk of the sample. And the rho xx equals 0 means there's no resistance, so there is no dissipation. And there's sort of these two descriptions, they conflict with each other. One says that there's no current in the bulk, and the other one says there is no dissipation, so there's no resistance. And the way to reconcile those two is to actually use this concept of one-dimensional channels, which I briefly discussed recently. So 1D channels on the edges of the sample. and the sample is insulating. So on the edges of the of insulating bulk of the sample. Let's draw the picture. So we have a sample. And in the bulk, we have a cyclotron motion, so all the electrons are localized in these cyclotron orbits. And on the edges, we will have these skipping orbits. And again, the same on the other one. So they counter-propagating chiral edges. So if we look on from the energy point of view, we can also redraw this diagram. So this is the x direction of the sample. So we can redraw now in terms of a potential energy experienced by the particles, and those are the boundaries of the sample. So those are the edges. And the potential would be like some potential there, maybe 0, and then it kind of steeply goes up as we reach the boundary. So you have like infinite barriers there. And you have this potential quantum well. So then if you have a Fermi level, let's say at this point somewhere, then we can also visualize how many states you have, because those wave functions are the strips which go along the y direction, and they separated by this by the delta axis. So each of those wave function strips are centered at a x naught, which is h bar k over EB. That k is in the y direction. We can then just draw them here. So each state is a wave function, and then they separated by these delta axis, and so on. So the bulk is insulator. So all the states here are filled in the bulk, and on the edges, those states can conduct electricity, and they will conduct when you apply the electric field. So when you introduce the change in the chemical potentials on the two edges, so delta mu, because of the electric field. And let's say if we apply electric field, maybe we increase it along this direction and decrease it along this direction. So you have a delta mu like a so. So this is delta mu. And so only those states will contribute to transport. And because it's essentially a one-dimensional conductor, so you can, using our derivations for conductivity in 1D channel, so it's a 1D conductor with a conductivity of one mode is E square over H. The modes are counter-propagating, as I said, so there will be no voltage drop along the direction of the current. That's quite essential. So let me draw this whole bar again. And let's say we use this contact to introduce the current. So the current is injected from this side, and it exits from this side here. So if you start, like, if the bulk is insulating, so the bulk is excluded from transport, we only consider the edge modes, and I'll use a different color here. So the mode starts to propagate on this side, and it kind of keeps going all the way here, and it kind of propagates this direction. So you will have a voltage drop of a delta V here, and then it keeps going, and now it counter propagates, it goes in the other direction. So here you will have then the minus delta V voltage drop on this side, and they will cancel each other. So delta V plus minus delta V will be 0. So there is no voltage measured on those terminals. So that's why you will get this Rxx 0, rho xx 0, and sigma xx 0. In the y direction, to consider this quantization in this direction across, you would need then to compute the current in the y direction, which would then allow you to calculate sigma xy and the rho xy. And to calculate the current, we can use the Drude model sort of in a combination with the Landau levels, with the states coming from the Landau levels. And the way to do it, so our the current is the carrier density times the electron charge times the drift velocity. And so the drift velocity is a bit tricky when you have a magnetic field. There will be two components of motion. There will be cyclotron motion, and then there will be this motion because of the presence of electric field. Without going into derivation, I can write you down. So the drift velocity in this case will be 1 over b squared b cross E. It's a nice exercise to do the derivation. When the electric field is inhomogeneous, like in our case, so there will be some big inhomogeneity in those regions because the potential is inhomogeneous. You can then rewrite it for the inhomogeneous field as 1 over b squared b cross gradient of potential. And this drift velocity, it will be in the y direction, because y is perpendicular to magnetic field and electric field. So we can then calculate the current along the y direction. Again, using just instead of counting these modes, we can just do the integration in our limit, which would then be the integral of, and we do the integration in the dk, which is the same as the dx because of this definition. So we have this x naught is h bar k over eb. So the separation in the x, it also means there is a different momentum for each momentum in the y direction for each of those stripes separated in the x space. So then we take the integral with our velocity in the y direction, which is a function of k. And then the integral would be, so let me briefly say it. So dk is dx eb over h bar. That's from this one. Then we can plug in the numbers. So we have dx eb over 2 pi h bar. And then the velocity, we take this one here, which would then be 1 over b dv dx. The gradient in the potential there along this one. So we put that one there as well. 1 over b dv dx. And sorry, this one goes here. 1 over b dv dx. Then, so we have, this one is h. We have e here, so it's e square over h. Then the b cancel, and you have the gradient will be just the voltage difference we have applied, so times the delta v. And we got our quantization, so e square over h.